Diffusion into a falling liquid film, solid dissolution problem. In this, the first assumption is that liquid B is flowing in laminar motion down a vertical wall as shown in the figure in the next slide. See, this is the liquid film, liquid actually, which is flowing down, and this is the near wall. This is a parabolic velocity profile of the fluid B. So this is fluid B, and this is a solid A, which is slightly soluble wall made of A. See, the concentration profile or the diffusion is very small when compared to the entire film. Solid A dissolving into a falling film of liquid B. This is liquid B, this is solid A. Solid A is dissolving into liquid B, moving with a fully developed parabolic velocity profile. So this is fully developed parabolic profile. From the figure we can understand that solid A dissolving into a falling film of liquid B, moving with fully developed parabolic velocity profile. The film begins far enough up the wall so that Vz, here actually Vz means V subscript Z means velocity Z component depends only on the Y for Z greater than or equal to 0. For Z between 0 and L, yeah, we have seen that solid part A starting from Z is equal to 0 and Z is equal to L. The wall is made of a species A that is slightly soluble in B. For the short distances downstream, species A will not diffuse very far into the falling film. This is what is another intrinsic assumption which we have to understand. That is, A will be present only in very thin boundary layer near the solid surface. Therefore, the diffusing A molecules will experience a velocity distribution that is characteristic of the falling film right next to the wall. Y is equal to 0. The velocity distribution is given by the equation below, considering cos theta is equal to 1, that is theta is equal to 0 degrees, and x is equal to delta minus 1. Delta is, I think, film thickness what we have seen. So this is a velocity profile equation. Vz is equal to rho g delta square by 2 mu into 1 minus y by delta whole square, and upon the simplification, means upon the expansion, we get this particular equation. But y by delta itself is small, then y by delta whole square is again still small. That means the second term in the right hand side can be eliminated and you are left with only this particular term. That is this particular term. You are left with only this particular term. That means this term can be neglected. Okay. So our equation can be written in terms of rho g delta square by 2 mu into 2 into y by delta. So the delta cancels, 2 to cancels. Okay. Yeah, this is what is the approximation. And then finally, and the concentration profile can be taken this way. Ay dou Ca by dou Z is equal to dAb dou square Ca by dou y square. That means now we are able to understand Vz is also present. At the same time, mass transfer is also present dAb. This equation is to be solved with the boundary conditions. These are the boundary conditions. Boundary condition 1, z is equal to 0, Ca is equal to 0. Y is equal to 0 and y is equal to infinity. Why y is equal to infinity? Because in the y direction, there is only small film where we can understand diffusion of A is there. At y is equal to 0, thin boundary layer, Ca is equal to Ca naught. But at y is equal to infinity, we assume Ca is not available at all. So further, you can actually refer the book written by Bird, Stewart, and Lightfoot. See here in the top section, what you see, the section in the second boundary condition, Ca naught is a solubility of A in B.